requirement at this point necessarily in your life to simplify it. In fact, actually, I think you'll find many applications where we actually may not want to multiply it out what you get. You may actually want to leave it the way it is. So I'll take a volunteer because it's still new here. I don't want to like call out anybody. Someone willing to, maybe someone has to take an AP. Willing to step out and say what they think it is based on our reason on the last slide. Yeah, go ahead. Yeah, give me a second step in there. So you did.
So I did the power rule for
okay, so.
times 4 and minus 5. Oh, so the second term.
Okay.
Times the derivative with exponent.
Which is? Good. Yeah, and that's correct. And if you want to say 12 times that, or if you want to multiply it out, that'd be fine. But it's certainly true that we've done the job of taking the derivative. If you want to clean it up a little bit, that's fine. All right, we're finally ready to say it in a box. We're gonna put it in a box, right? Isn't that how we roll? Okay. But now, before I actually tell you what it is, can you tell me what it is? What do we do here? We're taking like the derivative of something. I mean, how could you formalize what we've just done? Albert, you want to track at this?
Yeah. So it's Alright, sorry. It's n times the equation to the n minus 1 times the derivative of the.
Now I realize I've only given you examples of how to use the power rule, so this is a little bit tricky. But the bigger idea I guess I want you to see is there's an inside and an outside function, and it doesn't necessarily. The power rule doesn't have to be at play necessarily. Like in a minute, we're going to do like the sine of the square root of x or something, right? And then your rule maybe doesn't make sense. So sorry, it's my bad maybe not for providing enough examples before I asked you to generalize. Keep in mind that this looks like what kind of thing from pre-calculus? This looks like a certain action that you might have taken with functions. What's the word?
I remember this one with finding zeros.
Finding zeros? That's not what I was looking for. but thanks for your volunteers. It looks like again, this language of like the inside and the outside function here. What kind of thing do I have from? What kind of object do I have from?
It's like I forget.
Nested functions is a great name for it. That's not what we usually call it, but yeah, it looks like we have like the result of a composition of functions, doesn't it? Doesn't this look like f of g of x or something? Doesn't that look like what we've done? We like have a function inside of another function. And that is like what we're talking about when we're talking about the chain rule. So my question is, what then goes here? Based on our like informal discovery so far. Talk with your group for a second. See if you can fill in the blank, and then I'll show you here the answer in a second.
Okay, well, let's say the f here. Oh, the g is 4x. It's just the derivative of the x. That's to say it's the derivative of f of g times the derivative of 5. Round here. F prime of it's just prime. Right? So you got all sorts of thinking back. What I'm looking at now. Look, so the meaning of 3 something squared is just f squared. It's going to be an f squared. Right. And inside that is going to be an f prime of x. Inside that f prime of x is like
All right, you ready? All right, so you all want this. I know you do. You got it, right? You guys are excited about it, I can tell. You only pick on someone random. I like doing this. Let's put, no, have I heard Christina? Yeah, I heard you. Go ahead, Christina. What do you got? What do you think? Did you guys come up with something?
Yeah.
I'm anxious to hear.
Is it derivative of f of x times derivative of g of x?
The derivative of f of x times the derivative of g of x. Close. I need a little more, like, because that's not what this is it? Is that if g of x is the inside function and f is the outside function, this is not the derivative of f times the derivative of g of x. This is definitely derivative of g of x. That's true. I agree with that part. But this is not the derivative of f of x, is it? Not quite. You want to correct me, Grace?
It's the derivative of f of g of x?
Yeah, times g prime, right? Is that cool? You just call timeout?
Yeah.
Okay. By the way, this works even in situations where you don't think it's necessary, like x squared. X squared is a composition of two really dumb functions, x squared and x, right? So technically, like if we took the derivative of x squared, it'd be 2x, and then you'd be like, well, wait, don't I need to multiply by the derivative of the inside? Well, sure. It's 1, right? So it is actually something that's always been at play, even when we're not quite aware of it. So, just thought I'd share that. It also makes a comment on this slide that this is one of the most missed ideas on this unit test, the forgetting of the chain rule. It's just everywhere. Once we start introducing it now, you'll see it everywhere. Basically, your default should just be like, have I thought about the chain rule yet? I know you don't think that's true of your life, but it will be true. Marcus, how are you feeling?
X squared, g is x.
Okay.
Yeah. Okay.
Are you good? Time back in here. All right, we're back at play. All right. Anybody else need to call timeout? Albert's like, no, let's move on. I'm ready. Gives me more. All right. All right. Let's try a couple that don't look and feel the same way as the one we've just done. So I just promised a second ago that we'll do like the sine of something like this, right? So what's the sine of x squared minus 4? Let's take the derivative of that. Take a second to do that with your group. If you're ready to do these other ones, you're welcome to go on too. But so think about the rule you just said. Be really careful about your compositions. All right, someone willing to give it a stab, the first one? So, Stephen, you did take AV yet, right? I want like fresh blood. I want uncooked minds. Okay, go ahead.
So is it cosine of x squared minus 4?
Okay, I'm taking the derivative of the outside. Okay.
Times 2x.
Times 2x. Do you agree? People over there? My AB people? You should be like the certifiers today. Yes, I bless that. Okay, good. That's correct, right? So this is how this feels. Now we don't even have the outside function isn't involved. The power rule isn't involved in taking the derivative of the outside function. So I think we're good. That's great. Good. Give this one a try. Why is this one? Why is there a dagger in front of this one?
Because it's squared.
Well, because it's like a tricky one. That's true. Yeah. But why is it tricky? Have you already seen through it yet? Keep in mind that by cosine squared of 3x, we mean cosine of 3x squared, right? All squared. So keep in mind what the outside and inside functions are and stuff. Well, there's another dagger. That's not the dagger. I mean, if you haven't encountered the dagger, you will in a second, right? I mean, give it a try as you differentiate.
It's gonna be a 3-part thing.
Or is it cosine then g of x?
Yeah, I think Yeah, I think we need to apply the chain rule twice here. I hear some people mumbling. So keep in mind, like when you go to take the derivative of cosine of 3x, that's its own problem, right? Isn't it? Like I could have asked that question. Figure out what that is. All right, we're just gonna like write down the answer. You can see whether you got it, and maybe we can show the work in between too. But I thought this would be a unique opportunity too, to just like put one of our parents on the spot. What do you guys think of that?
Yeah.
All right. Oh yeah, yeah. There just happens to be a parent in the room. So let's see if you remember your calculus, Mr. Bernstein. Think you can do it?
Negative 6 cos x, cos 3x.
Is that what you guys got out there? Very good. Wow. Did you know your dad could do that? Good. Wow. That was amazing. Whew. He remembers the chain rule, even in a dagger situation. That was incredible. Now let's make sure that works. You want to see some intermediate steps there? All right. We'll produce them then. Go ahead.
Man, I had the first correct, but not the second one.
If you didn't get that, then make sure you do, because that is correct.
Yeah. 3 negative sine x. Yeah, negative 3 sine x. Now that I made it intermediate, I might show myself.
Yeah, that's the trick, isn't it? How did you learn that? I did something you must have.
I just have my own. It's just that minus
Actually, do you remember that?
All right, hopefully you've had another, I just like to have you struggle a little bit. Do you agree that, again, to take the derivative of this, we're taking the derivative of this function, cosine of 3x. I'm going to put parentheses everywhere here just to make it obvious that we have like three functions at play here, and we'll have to use 2 chain rules. So the derivative of the outside disrespecting the inside is 2 times the inside. Yeah? So far so good? The penalty for like ignoring the complexity of the inside is you have to multiply by the derivative of the inside. So we still haven't done that. We need to multiply by the derivative of the cosine of 3x. So in fact, you can write that off to the side, cosine of 3x. New problem, find the derivative of cosine of 3x. That's also not trivial. What is it? Well, it's negative sine of 3x, right? Oh wait, times 3, right? That's another chain rule. Isn't that like if I asked you separate problem off to the side, what is the derivative of cosine of 3x? You'd be like, oh, that's a chain rule problem. It's negative sine of 3x times 3. Isn't that what you would say it was? And this is in fact this, of course, if you simplify it. Is that good? Yeah. We actually really do have to and you could do this another time if you needed to, right? Maybe you're getting an idea of why a chain rule is a good name for this. Yeah. So the chain rule is you're taking the derivative of the outside here, so it's 2 times just the inside function as it normally is. So you're good with that part. But then the next thing you're supposed to do is multiply by the derivative of the inside. And I claim that the derivative of cosine of 3x, which was the inside, is this. Do you want to work that off to the side? What would that be? Well, this is its own chain rule problem, isn't it? Isn't that negative sine, the derivative of the outside, disrespecting what's in the inside, and then afterward multiply by 3? That's exactly what I wrote here in the bracket. Okay, great. And then if you haven't already tried it, go ahead and do the AP style number problem down there with no functions available, just with no numbers. Yeah.
Why couldn't you just have taken the derivative of cosine squared instead of and then
What is the derivative of cosine squared?
negative 2 cosine x cosine x.
Wait, say that one more time.
Negative 2 So what, so it would be -2 times, -2.
Oh, did you say just find the derivative of cosine squared,
Yeah.
x first,
Yeah.
and then plug in 3x or something? Is that what you're saying?
Yeah.
I think you'll get not this though. Am I right?
So I got that.
Where'd the extra 2 come? The extra product, the extra multiple of 3 come from in yours?
Times the derivative of
No, I think didn't you just say you're taking the derivative of cosine squared x, which is I think you said is 2 cosine
-2 cosine
sine
x.
x.
Sine x.
Okay, and then you just said you're going to plug in 3x.
And plug in 3x and then multiply that by the derivative.
Absolutely, perfect. Yes, you can do that.
Okay.
That is in fact what we did too. Yep. Yep, you can do that. Did you get it? I don't know, just in case you need it. I don't know. Just for fun. You might, there might be some things you don't need. Maybe there are some things you need. Maybe the things you don't need. I don't know. I will just say, like, AP truly does love this kind of problem where you're like doing the thing in the abstract.
Maybe G prime x.
Derivatives to the outside. As if the inside is just like x, right?
So go back to that G prime of G times G prime. The chapter is 2 lines on there.
Like a third of sine of this, right? What I want to hear is what is the derivative?
F prime of G x. So F prime, I get it. Really good enough. Is -1. Times G prime of x. Go back to your place where you have the formula times G prime of x.
So you take the derivative as if this is just
It's
x.
going to give us 7.
So that's what the f prime of g is, right? F prime
And
of
then
g.
plug it into F prime of
G is the same.
Okay, here, let's go back to the formula.
Yeah.
So here.
All right, let's work this out here. So f of g prime of 3 is equal to f is the outside function, right? So we want f prime of g of 3 times g prime of 3. Let's work this out slowly. G prime of 3 is given to us. That's wonderful. It's 5. What's g of 3? 7. Isn't that really convenient? Do you see people who are asking why I was giving you this? Why now? You see? Do we need f prime of 7? In fact, yes we do. And it's -1. So did you get -5? Does that make sense? Is there anything up there we didn't need, by the way? It would have been a cooler problem if I gave you additional information you didn't need. That would have made it better. Yeah. In fact, a lot of times AP will do that. You'll get like, huh? We didn't use f of 3 ever? Perfect. Good. That's what I like. Okay. Good. Yeah, you think you might need that along the way? You don't. Okay. So perfect. Unless someone asked you, also find the tangent line to this f of g, right? And then you'd need this value and the derivative value. That'd be kind of a fun problem. This makes me think of that time when we did like the product and quotient rule too. Do you remember those problems? We gave you different values of the right? I think we did that on the test even, didn't we? Didn't we? One of those. Here's another alternate form that I think will be useful to us. This is the same rule. Verify that it is in fact the same rule, written in Leibniz notation instead. So dy dx is our favorite way of writing the derivative here. That makes sense. Equals this times this, and that actually even makes sense too. You kind of feel like, oh, well, I think I know how fractions work, and that makes sense. But does that make sense in light of what we wrote before? I think it does, actually. Let's use f's and g's again. df dx is equal to df dg times dg dx. Isn't that in fact what we were writing before? Isn't it the derivative of f with respect to g of x? As if g of x is the independent variable times dg dx. And then when you write it that way, you're almost like, oh, well, actually, that kind of makes sense because I understand fractions. So another advantage to Leibniz notation. Now keep in mind that, yeah, I mean, they're not They don't work exactly like fractions, but we'll go with it. Okay. Huh? U is right now just playing the role of a dummy variable in the middle, right? Just like G is kind of the inside function. G and U play the exact same role. Exact same role. The inside function, if you like to call it that. So let me just illustrate, we did this one already before, but let me just illustrate why this makes sense in the context of one we already did. So let's let U be x squared minus 4. That is the inside function, okay? And then what do we need to compute? Well, we need to compute dy du and du dx, and then we'll see if we actually get the same thing we got before. Dy du, do you agree, is the original function, which is, by the way, is the original function sine of u? I think it is. So what's the derivative of sine of u? That is the original function y with respect to u. And the answer is cosine u. Do you agree? With respect to u, the derivative of sine of u is cosine u. Du dx, that is this thing here, right? We'd like to take the derivative of this with respect to x. Du dx is equal to, well, I think I've done that one before. It's just 2x, right? And now, what are we claiming? We're claiming that the overall derivative of the thing we want is the product of these two things, dy du and du dx. And it is, right? It's 2x times cosine u. But remember that u is x squared minus 4. And I think that's the example, that's the answer we had earlier, isn't it? Go back and look if you're not sure, or just do it again fresh. That might seem like convoluted to go through that. I just wanted to illustrate why this notation also makes sense here. Like obviously, in practice, if you don't need to write all this stuff, you won't, right? But just write down the answer is fine. But I think you will find that to be, there will be times and places where you'll find this to be a helpful formulation. Let me just throw one more curveball at you, if I'm allowed in one lesson on the chain rule. You've already like, that was enough actually for today. No. You ask and we deliver. Here we go. I'd like to say something, if you can handle it, about parametric functions for a second. I know. Head open knowledge. Okay. All right. Here we go. So just because it's a cool time to introduce it here when we're first talking about the chain rule, and there are some probability homework that requires too, so there's that. So keep in mind, this is exactly the chain rule as I had it on the previous slide, except instead of U, I put a T. Is that fair? It's just a letter. It's just a letter. So another way to write dy dx then would be to write this. Do you see why? Again, use your fraction skills. That you can reformulate the right side of this as this. Yeah? If so, then dy dt and dx dt take on new meaning to me if I'm in the context of parametric equations. That is, I have a function of t and another function of t to give the x and the y coordinates of like parametric motion, so to speak. So, for example, here's a parametric curve, and I'd like to find dy dx. That is arbitrarily a slope with y with respect to x of any place on this curve. By the way, this I should have asked before I showed you the picture, but did you know this was an ellipse? I think maybe you've worked with parametric equations a little bit before in pre-calc, I hope so. By the way, we're going to have a whole unit on this toward the end of the year. So, all right, so what is dy dx then? Well, it's dy dt, which I think I know how to compute. Can you find the derivative of this with respect to t? I think you can. Divided by dx dt. And my justification is the chain rule says that that's true. So find each of those and then just stack them, right? Give me the derivative of this with respect to t. No tricks here. Give me this, the derivative of this with respect to t, and stack them. And that'll be like, that'll be with respect to t. So the top one is, anybody want to take that? What is that? What's the derivative of 2 sine t? Should have known this on the last test even, right? 2 cosine t. And on the bottom, negative, 3 sine t. And actually you could write that another way if you like, if you want. You could write negative 2/3 cotangent t if you like. Good. And then if you want to try this at different points, for example, what do you think the slope at t equals 0 is? It doesn't exist. Am I right? If you plug in 0 for t, does the slope not exist? Try t equals pi over 2. What do you think the slope is? 0. Is that what you get over there? Yeah. Okay, so now you could try some other places too. Try pi over 4, for example. What do you think the slope is? What will it be? Cosine and sine of pi over 4, I don't know what they are. I have no idea what the cosine of pi over 4 is. But I do know that it's the same as the sine of pi over 4. Just geometry class. So I think that's going to be what? What's the slope there at x equals t equals pi over 4. It's negative 2/3 there. It looks like it maybe. Okay. So we're having fun with parametrics now. You didn't see that coming. Try one more if we can. Yeah, we have a minute. I think this is my last slide, so we're good. So try that one before you head out. Lots of fancy language. Just do the thing we just did, though, right? By the way, I don't think I needed to tell you root 2 comma 1. I just was being nice, right? Go all the way. Find the tangent line to this curve, not just the slope.
Now past that, we simplify that just a tad. Take that liberty. We can plug it back.
You got all this stuff. Try this one. See if you go.
I got 2 over 2 whatever you want.
Yeah, yeah. I mean, eventually you're going to plug in pi over 4, so if you want to simplify it, that might make it work easier.
Yeah, 2 over 2. Divided by 1. That's what tangent of pi over 4 is. It's just 2 over 2. Oh, I know. Put it in a line here. Yeah, line.
That's a good place to be, I guess. I don't know. What do you get when you plug pi over 4 into that?
Same thing. Yeah.
Anybody? Anybody? What do you get? Root 2? All right, so take the slope, use the point, write an equation, the tangent line, and do your homework. Take it easy, Raphael. Have a good one. Bye, guys. Take it easy. Happy Monday. Yeah.